When you write a simple script, procedural code works fine. But as a code base scales to thousands of lines, disorganized logic weaves together into a fragile, collapsing knot. A single change in one function breaks seemingly unrelated features across the system. To build at scale, engineers require a specific structure that prevents raw data exposure and stops logic duplication. Object-oriented programming, or OOP, provides this structure, shifting focus from a sequence of instructions to a network of independent entities. In Java, this architecture relies on 4 pillars: encapsulation, inheritance, polymorphism, and abstraction. These concepts are the rules of the system. They dictate where object boundaries are drawn, how structural hierarchies are formed, and how execution is resolved while the program runs. Mastery of these 4 principles provides the foundation required to maintain a codebase as it grows from a few files to millions of lines. System design begins at the level of the individual object. If an object exposes its raw data directly to the outside world, any external system can overwrite that state, leading to unpredictable behavior. This diagram represents an encapsulated class. On the left, variables are hidden, declared as private to block direct external access. But external systems still need interaction. We solve this by exposing public getter and setter methods on the right, which act as authorized entry points. Public setters allow engineers to embed validation logic before an internal state is changed. An if statement can check that a new age value is a positive integer before the update is finalized. Java enforces these boundaries at the compiler level using 4 access modifiers. The 2 extremes are private, strictly confining access to the exact same class, and public, granting access from anywhere in the application. By locking down data and routing all requests through validated methods, encapsulation ensures an object remains in a consistently valid state. Once individual objects are secure, the next architectural challenge is redundancy. In a large system, dozens of different objects often require the exact same foundational behaviors. This chart illustrates inheritance. By using the extends keyword, a subclass, shown here as class B, automatically acquires the properties and methods of superclass, class A. This establishes a strict ISA relationship. If you code an animal class with an eat method, your dog class extends it because a dog is an animal. The dog object now uses that logic without you writing it twice. As shown in this diagram, these hierarchies can stack deeply. Multi-level inheritance forms a vertical chain from class A to class B to class C, passing features down through multiple generational levels. This next chart displays hierarchical inheritance, where a single robust parent class, class A, serves as the foundation for multiple diverging subclasses simultaneously. When building these chains, a child class will occasionally declare a variable or method with the exact same name as one in its parent class. To navigate this naming collision, Java provides the super keyword. Calling super tells the compiler to bypass the child's implementation and explicitly target the immediate parent class's memory space, ensuring the original logic executes. Conversely, engineers sometimes need an architectural stop sign. That is the final keyword. When you declare a class as final, no subclass can inherit from it. It severs the ability to extend the class, securing the logic from being altered. Inheritance eliminates duplicated logic across codebases by centralizing common behaviors into singular parent nodes. Rigid hierarchies can become restrictive. Complex systems require objects that share a base structure but behave differently depending on their specific context. This flowchart maps polymorphism, the separation of a method's definition from its ultimate execution. There are 2 distinct tracks, compile time and runtime. Focusing on the left branch, compile time polymorphism is achieved through method overloading. If you write different add methods, the compiler analyzes the parameter signature, the number or type of inputs provided, to determine which version to execute before the program even runs. Moving to the right branch, we find runtime polymorphism achieved via method overriding. This is the mechanism for dynamic behavioral adaptability. It relies on a mechanism called dynamic method dispatch. Look at this representation of the JVM memory model. On the stack to the left, we create a generic reference variable of type animal. On the heap to the right, we instantiate a specific dog object and connect them with a reference pointer. This creates a tension. The reference type says this is an animal, but the actual object in memory is a dog. Which sound method runs? The JVM ignores the generic reference at runtime, tracing the pointer directly to the heap to execute the dog's overridden method. Dynamic method dispatch allows developers to write code that processes generic categories of objects, while the JVM adapts the execution based on the specific entity encountered. To fully decouple a system, developers must separate what an object does from how it actually achieves it. This diagram shows how abstraction hides implementation details. On the right, an abstract class offers partial abstraction, containing programmed methods alongside empty ones that subclasses must complete. On the left, an interface provides full abstraction. It is a strict architectural contract containing only empty method signatures, dictating no behavior of its own. Think of an interface as a blueprint. A vehicle interface simply states that start and stop methods must exist, leaving the slots empty. If a car attempts to implement this, the compiler rejects the code unless explicit logic is programmed for those exact slots. The benefit is modularity. Another part of the system doesn't need to know if a vehicle uses a key or a kickstart. It only needs to know that the vehicle interface guarantees those functions are available. Abstraction enforces system-wide compliance, allowing thousands of components to communicate through verified contracts. The 4 pillars of OOP function as interlocking components of a single machine. First, data is sealed inside individual class capsules. This encapsulation acts as the baseline armor, protecting internal object states from corruption. These secured objects are then structurally linked, sharing common properties to reduce logic duplication. This hierarchy allows the Java virtual machine to dynamically shift execution logic at runtime, selecting the correct method based on the object's actual type. All of these shifting trees are governed by strict contracts that ensure absolute predictability throughout the network. By mastering these 4 principles, a programmer moves from writing sequences of instructions to architecting robust and scalable software systems.